All right. Hello, everybody. My name's Stephen Galbraith, and I'm very happy to welcome you to this online celebration of 40 years of elliptic curve cryptography. I'm really happy that we've got Neil Koblitz and Victor Miller here to give talks about their work and to answer questions and discussion around what's been going on the last 40 years. There's a Zulip chat if you want to put questions in, and I will direct them to speakers. We're going to do the talks first, and then the questions after that. Then there'll be a short break, and then we'll have Dan Bonnet for a talk, and then Kristen Lauter, whose talk's going to be a pre-record. But she may be live for questions afterwards. All right. I also want to put a big thank you right off the front to Tanya Langer, who's managing the YouTube and the presentation system. And this event would not be happening without Tanya's help. So thanks very much, Tanya. So it's 2025. And we have to cast our minds back to 1985 when two things happened. So at the crypto conference in 1985, Victor Miller presented a paper suggesting to use elliptic curves for discrete log cryptography. And at the same time, more or less, Neil Koblitz submitted to Mathematics of Computation a paper also proposing elliptic curves for Diffie-Hellman type cryptography. So Koblitz's paper appears in 1987, but if you go back and check the publisher version, it says submitted 1985. So it's pretty natural to take 1985 as a beginning of elliptic curve cryptography. And so here we are, 40 years on. It's a chance to reflect and to hear from Victor and Neil and others. And yeah, seems like a good idea to get together online. And the reason why it's online is mainly because I wasn't interested in traveling anywhere. So, and I'm living in New Zealand, so here we are. All right. Well, first off is Victor. I was joking before that I can use the same introduction for both Victor and Neil. Victor studied at Harvard. He's won the Levsham Prize and the RSA Prize for Excellence in Mathematics. But I will personalize it slightly. He studied at Columbia for his bachelor's degree, and then Harvard for his PhD, which you'll spot the difference when we come to Neil. All right, I'm going to shut up and hand over to you, Victor. Go for it.
Okay, thank you very much, Stephen and Tanya. I really will enjoy this, and there's a lot more I could say than in half an hour, but I thought originally I titled this Elliptic Curves of Cryptography, a 40-year perspective, but as you see, I changed it to a 60-year perspective. I'm giving away my age because basically there we go. Did I get lucky? So I have a quote from, it's been attributed to Louis Pasteur, and I won't read the French, even though I can read it, because I'm sure any French speakers would probably have conniption hearing my pronunciation. But basically, it's usually rendered in English as fortune favors the prepared mind. And so what I want to talk about is the people who influenced me and prepared me for this. And when thinking about this, basically, well, that shows me then. And so I was at Columbia from 1964 to 1968. And one of the important things I studied is Columbia had a mathematics sequence, which was called their C sequence. It was ostensibly calculus, but it was really what I call mathematics for prospective PhDs, because basically everybody who survived the course either got a PhD or there was one got it, in math, or one got it in physics, another an MD PhD, but that was it. The first year was taught by Serge Lang, and the second year by Lipman Bears. Serge Lang became my advisor. Now, a lot of people may have heard about Serge Lang because of his books. He was definitely a singular force within mathematics. But what was interesting was that it started in September, and in October, he gave us an exercise, which it turned out the exercise pertained to heights and elliptic curves without mentioning them. And because it just was on his mind. So here's Serge Lang. And he actually had in one of his books, one of his many, many books, which he wrote, I've lost track, at least 40, was about elliptic curves. And he did say it's possible to write endlessly about elliptic curves. This is not a threat. But as you see, in May of that year, he had a seminar Bourbaki article about bilinear forms of Néron and Tate. And I've given an excerpt here because what he calls his fundamental lemma over here, that was the exercise that he gave us. He just gave it to us in an abstract form without really mentioning what the motivation was. But I realized in looking at this that this was in sense, and it turns out that this lemma and heights on elliptic curves were actually of great importance in the analysis that I later gave. So that's why I think about that. But when I was at Columbia, there were two other professors there who had a great impact on me and actually helped, in some sense, the intellectual preparation for all of this. First one was Lipman Bears, who's on the left. He taught, besides the second year of that, he taught complex analysis and the Weierstrass P function, which he used to joke that it's not very hard. He said the hardest thing about the Weierstrass P function is being able to write the Weierstrass P. And on the right is Pat Gallagher, who essentially taught me analytic number theory. In some sense, when I registered for the course, it wasn't meant to be that, but for various reasons, because something important had come up, he completely changed what the course was. And I still have his notes today. They're just wonderful notes. But the other part of it, which I think, at least as far as me, is I was always interested in computers and computation. But I'm old enough so that there was no computer science department at Columbia or almost any other school at the time, but there was a computer center. And this is what computers looked like in those days. There was this huge mainframe, the IBM 7094. And over here is the room where I hung out because we were only allowed one run on the computer every 24 hours. So I used to sit in this very table. In fact, this could have been me because I had a briefcase just like this, so I don't know if that is me. And poring over my printouts, so that sort of changed my working habits. But at the same time, I came across this book called Elementary Cryptanalysis, which sort of got me interested in cryptography, even though in a simple way. And the other book, why does it keep jumping, is Knuth's Art of Computer Programming, which came out in my senior year. And I think what this did is this gave me an appreciation for for the actual for the actual time and that computations take, the time and the space and actually the optimization which was necessary. So I got to Harvard the next year in 1968, and and that's actually where Neil and I first met, because Neil was a senior at the time during my first year of graduate school. And in my first year of graduate school, there were a number of great courses I took, but the ones that were really influential in all this, the very first semester was the last course taught by the great algebraic geometer Oscar Zariski, who taught actually a rather down-to-earth classical course about algebraic curves and linear systems and so on, which again really prepared me for that. The second semester was taught by his student Robin Hartshorn, which basically used the scheme theoretic idea of it, but it gave, so basically having both points of view was really important. And the next year, I took a course in ring theory from Richard Brouwer, again, another giant of 20th century mathematics, and Lars Alfors on automorphic forms. Now, automorphic forms and modular forms are intimately connected with elliptic curves. But again, did this influence me? Yes, it did. Now, the next year, unfortunately, I didn't go there, but I had to show this picture because I think it's very important to show what was going on. So the next year, Oxford held a conference of computers and number theory. And if you actually look at this, you can see pictures of a number of prominent players in number theory. Some of them did computation, and some of them were just computation curious, shall I say. But you can see everyone from L.J. Mordell to Helmut Hasse to John Tate, Oliver Atkin, Brian Birch, Ian Castles. There's a whole bunch of amazing historical photographs here. But what was interesting was when I got to Harvard, is that I at the time was the only person there, whether graduate student or faculty, who really had any facility with computation. Later, a few years later, Joe Bueller entered as a graduate student, and he and I were sort of the two. And I remember that at one point I actually made a computation which actually showed the multiples of points on an elliptic curve, and you could see that the digits formed a nice parabola, and which is essentially the quadratic thing of Tate height. And Jean-Pierre Serre took a snapshot of Tate next to the Tate height, because this was, in some sense, the first time he had actually seen it as a parabola. He knew it was there. But what was really important, so I actually took off 2 years because I was tired of being a poor graduate student. I think any graduate student can sort of sympathize with that. And I went to work doing computer programming at IBM in a place called BB&N. But I came to the conclusion that I really had to go back full time in order to finish. And that summer of 1972 was an incredibly formative summer because Professor Tate, John Tate, gave a 6-week seminar, which met 3 times a week, taught mostly by him, but also taught by Barry Mazur, who later became my advisor, and John Coates. And in fact, you can see over here on the left, my first notes from the elliptic curves. So this is where I really learned the ins and outs of the difficult stuff about elliptic curves. And the other thing that Tate handed out there is what was called as Haverford notes, which people who look at elliptic curves may now see because later Joe Silverman actually published them along with his commentary on these notes. But this was just a privately circulated bunch of notes, which were done by, in TypeScript. And then later that summer at the American Math Society summer meeting, Tate gave one of the main talks about the arithmetic of elliptic curves, which was, he had a handout, which was something like, I would say like 25 pages, along with I think, an 8-page bibliography. And which was later published in Inventiones Mathematicae with hardly any changes, which basically summarized all the what was really known in some advanced way about elliptic curves. And at the time, there were only elliptic curves themselves as a separate study. Really, only was done by a handful of places. There was Tate and Mazur and some of their students at Harvard, and there was I guess Nick Katz and some of his students like Neil at Princeton, a few at Berkeley, a few at Oxford and Cambridge, and maybe in Moscow, and that was basically it. But it was about to explode, I guess. So when I was at Harvard, the next year, it sort of became like elliptic curve central because all of these people were there. Barry Mazur was my advisor, and Tate. And there were 3 long-term visitors, Brian Birch, Peter Swinnerton Dyer, and Jean-Pierre Serre. So Brian and I especially spent a lot of time talking every day because Barry had a very high-level point of view in terms of scheme, but Brian was a little more down to earth. And so the blending of them really, really helped. And so fast forward, of course, this is something that almost everyone here probably knows about. Only a few years later, the following paper appeared by Diffie and Hellman, but I say Hellman and Diffie because that's the order they're in the photograph, of New Directions in Cryptography. So basically that, this is the only the only mathematical slide that I really have, just basically giving the outline of Diffie-Hellman key exchange, which sort of revolutionized cryptography. And so immediately, a number of people started being interested in the commercial possibilities of it. And there were Ron Mullen, Scott Vanstone, and Gord Agnew at Waterloo, formed a company which I think underwent a number of different name changes. It was originally called Cryptech, then it was called Mobius. And they had done this because they were working a lot in finite fields, and they had designed and built a chip for doing fast arithmetic in various finite fields of characteristic 2, which then were really important for coding theory. But once Diffie and Hellman paper came out, they realized that this could be important for cryptography. And in fact, the Federal Reserve Bank of California had decided that they were going to use a certain, Diffie-Hellman in this field, f of 2 to the 127, to secure all their transactions. And later, that company actually ended up changing their name to Certicom, about which I'll say a little more later on. So what happened is that in 1983, Fujihara, who came to IBM, where I was working at the time, and he gave a talk called "How to Rob a Bank," because basically this was a reference to what I just said about the Federal Reserve Bank of California. And what the paper was about was a great practical improvement of possible discrete log attacks on the Diffie-Hellman system. So what happened is that Don Coppersmith and I were in the audience. I mean, I had known Don since he entered Harvard in 1973, and then he and I worked together at IBM. And he was very intrigued by this talk, and he started to think about it. So in fact, we would sort of chat about it all the time. And within, maybe 6 or 8 months, he came up with a devastating attack, which later was published in Fox, and then later in a longer form, evaluating logarithms in GF2 to the n. The import of it was that suddenly the actual discrete logs over GF2 to the 127 could be attacked in something like 8 seconds on the IBM mainframe. So that obviously killed it completely. But this got me to thinking. I said, well, the Diffie-Hellman idea is a wonderful idea, but, what could we do to repair it? So because basically Don showed that in general, that if you worked over GF2 to the n, which was very attractive, that the length would have to be very, very large in order to be immune from his attacks. So that year, I actually spent a year at the computer algebra group, where again I had been interested in computer algebra and computation for a long time. You can see me over there next to James Davenport, who's on the left, who in fact James was the one who did the programming for Don. So that's when I was working for that group, that's when I came up with the idea fleshed out for elliptic curve cryptography. But what started me thinking about it is I had been writing a joint paper with Jeff Ligarius and Andrew Idlisko, whom you see at the top, about counting primes. And I was the one who did all the programming and all of the actual computation. And this is the first really large-scale number theoretic computation that I had ever done. So I was visiting them at Bell Labs, and on Jeff's desk was a manuscript by René Schroff. And I saw the title of it, and I started looking at it, and I said, "Whoa, this is really interesting." And Jeff was rather upset about it because he had been on the program committee for Fox, which had rejected it. But I asked for a copy, which I got it. And because of my background in elliptic curves, I immediately understood, what Schroff was doing. And that started me thinking about, what could be done with elliptic curves. Now, another thing that influenced it, which I think Neil will mention, is Hendrik Lenstra's paper, Factoring Integers with Elliptic Curves, which also came out in manuscript form that was privately circulated around the same time. So basically, I wrote up my results, and the crypto conference was pretty new. This was only I think it's fifth year there. And this was you can see that there are not that many people here. There was the large chunk of all the people who were not in classified community who were interested in cryptography and attended that. But one of the things I said, because I know that when you're giving a talk, it helps to get your audience's attention. I said, if you have chips to do fast arithmetic and characteristic 2, don't throw them away. I have another use for them. So immediately I was collared by Len Edelman and Kevin McCurley and Scott Vanstone to ask me to tell them more about elliptic curves, which I did. And Scott immediately then pivoted his company to working on elliptic curves. And so the other thing that happened was that I gave the first talk about elliptic curve cryptography in December 1984, and Manuel Blum was visiting IBM at the time, and he challenged me to provide, since I said that it should be stronger than ordinary discrete logs, he said, why don't you give a reduction? And I realized that something like the Weil pairing, which I was very familiar with from my study in elliptic curves, would give that if it could only be computed quickly. And Eric Kaltofen, who was actually one of our visitors in the group, had done an interesting paper about computing with straight line functions, which basically sort of inspired my approach to it. So I wrote this paper, Short Programs for Functions on Curves, submitted it to Stock. It was rejected, and I decided that it was so obscure that there were only a handful of people who would really be interested in it, and I knew them all, so I just gave them all copies. And including later on in 1993, when I met Dan Bonell when he was a graduate student, I gave him a copy. Later on, because it was turned to be influential, I fleshed it out into a much longer paper, which was published in 2004, the Weil pairing and efficient calculation. And in fact, then I was in touch with Bert Kaliski, who was a graduate student of Ron Rivest, and he was actually the first to implement the Weil pairing algorithm in his thesis. He actually gives a listing in Maxima, for the code. And so then Scott Vanstone and Alfred Menezes and Tatsuaki Okamoto then actually used the Weil pairing to reduce them to logarithms in a finite field. I mean, in some sense, this was my motivation, but I mean, what they saw, which somehow I missed, is that because I expected the degree of the extension would be so huge that it really wouldn't be a factor, but they saw a case that I missed, which was in supersingular curves, which they were very interested in. But that actually got the pairing algorithm a little more publicity, shall I say. And then Gerhard Frey and Hans-Georg Ruck actually then talked about using the Tate pairing, which they could also use some of the algorithm that I had to calculate. So Gerhard Frey, again, one of the things that I found was that elliptic curves, cryptography actually gave an opportunity for people who are mathematicians to actually transition into cryptography. And that was so Gerhard actually then did that, started an institute, and I guess he was Tanya's advisor among other people. Then later, what really blew things up so I think in 1998 or 1999, something around then, Dan Bonet sent me an email saying, "Is it okay to put your unpublished manuscript on the Stanford website?" And I said, "Sure." And I said, "Why?" And he said, "Well, it has a lot of applications." So it turned out that the applications were to to give an actual practical implementation of identity-based encryption. And about at the same time, Antoine Jou used it to give a one-round protocol for tripartite Diffie-Hellman. This was considered important enough so that the three of them won the Gödel Prize for their work in 2013. And then, of course, there were there was a follow-up. So there were six conferences or workshops on pairing-based cryptography because it really blew up. But I will say that in a humorous thing, so you may know that there's something called CFAIL, which Alison Bishop had started, and they gave me their first annual Distinguished Failure Award for failure to publish this, which you can see the picture here. Now, the interesting thing, as I was looking at this, I actually found this thing on the web, dated May 5th, 1998, talking about how elliptic curve cryptography is one of these overhyped things which will probably only last 12 months. Well, I think they were wrong. Now, and in fact, in 2005, which is only 7 years later, it really made the case that the National Security Agency had the case for elliptic curve cryptography and made it an essential part of their Suite B system. And then, in fact, now today, TLS 1.3 only allows elliptic curve Diffie-Hellman for key exchange. I've sort of joked with people when they asked me, did I ever make money on this? And I said, no. And I said, I'm not greedy. I'd ask only 1/1000th of a cent for every use of elliptic curve cryptography, which would mean a lot of money. But and in fact, as I think that Dan will say, almost blockchain, almost all of them, to my knowledge, use some sort of elliptic curve based security, and most zero knowledge proof systems today use elliptic curves, even though there are a number that do not and are trying to, as with a lot of other things, people are trying to transition to post quantum. As I said, but the influence on elliptic curves, there will still be their isogenies of elliptic curves are a proposed post quantum method, and in fact, they're also related to isogenies. They're not abelian endomorphism rings. So I really, I hope I'm not running over and have a little time. So basically, the study of elliptic curves has gone from beautiful, but in someone's arcane piece of mathematics, an idea of major impact in cryptography. And I said, and it's a good reason to learn hard number theory. I really urge people to learn more number theory. And of course, I have to give the usual thing. The photograph of the Oxford conference is by Gilman and Soames, and Robin Hartshorn is from the Mathematisches Forschungsinstitut of Oberwolfach. And I hope I've kept the time.
Thanks very much, Victor. I can assure you, you've kept extremely well to time.
Right.
So that's awesome. I think we'll save the questions for afterwards. So if you can stop sharing, and then we'll Okay, welcome back, everybody. We've got Neil Toblitz now giving his talk. Neil, well, as you've heard, he overlapped with Victor briefly at Harvard, but he did things the other way around. He started at Harvard and went to Princeton for the PhD and has had a distinguished career in mathematics ever since. Neil, I'll hand over to you.
Thank you, Stephen, and thank you also, Tanya, for your tremendous work organizing this event. I'd like to start by sharing some reminiscences from long ago about the early years of ECC and related matters, and also give some remarks about what attracted me first to mathematics and later to cryptography. My plan of becoming a mathematician was set in stone essentially in 1956 at the age of 7, when I returned to the US from India, where I'd been in the 2nd grade in a school that had a more advanced math curriculum than back home in the US. So when I returned to enter the 3rd grade, my teacher was very impressed with my facility at multi-digit arithmetic, and she encouraged me greatly. So for me, math just ended up being the logical choice. It was the only area where I could do better than my peers. So the process of elimination is really what led me to mathematics. By the time I was an undergraduate in the late 1960s, I'd settled on my main area of interest in mathematics, namely number theory and related fields of math, such as arithmetic algebraic geometry. These were all areas in abstract mathematics. At that time, I was unfazed by the thought that I'd end up spending my career doing research that was useless, that is, barren of any practical applications. I knew what the famous British number theorist G.H. Hardy had written about number theory in his book Mathematician's Apology, published in 1940. He wrote, quote, "Both Gauss and lesser mathematicians may be justified in rejoicing that there is one science at any rate, and that their own," and he was referring to number theory here, "whose very remoteness from ordinary human activities should keep it gentle and clean." And here's G.H. Hardy sort of frowning about all this. When he said gentle and clean, he really meant free of applications, which in his day largely consisted of military applications. Hardy was a pacifist, and his view seemed reasonable to me 3 decades later, the late 60s, early 70s, when my student years coincided with the height of the genocidal U.S. war in Vietnam, which resulted in the deaths of an estimated 3 million Vietnamese people. And by the way, efforts were made within the American Math Society, including by some very prominent mathematicians, to get the AMS to urge mathematicians not to work on military applications, but those efforts failed. Then in 1974, I wrote my PhD thesis, which was a study of the p-adic properties of the Hasselbeck zeta function of an elliptic curve, or hyperelliptic curve, or more general curve or abelian variety defined over a finite field FQ. That zeta function codifies the numbers of points on the curve or variety over all the extension fields of q to the n elements as n varies. So given this thesis topic, there's still no reason to doubt Hardy's words about gentle and clean. The military was not going to come knocking on my door. Well, my interest in cryptography started shortly after I moved to the University of Washington in 1979 for my first tenure-track job. I had read, and like a huge number of people, been intrigued by Martin Gardner's 1977 article in Scientific American introducing the public to RSA. But it was teaching, not research, that caused me initially to want to learn a little cryptography. And here's the issue of Scientific American that included Gardner's famous article in its mathematical games section. One of the courses I taught was our Introduction to Number Theory. Traditionally, it had been taught as an introduction to rigorous proofs. And I thought that approach seemed boring and pointless to almost all of our students. And so I saw in Gardner's article an alternative focus for an introductory course on number theory. In fact, almost none of our students intended to become theorem-proving pure mathematicians. And after reading Gardner's article, I saw that focusing the course on the mathematics of RSA would connect number theory to the spy versus spy world of cryptography. And that would be a much more effective way to arouse the interest of students. And here, Spy versus Spy was a cartoon series that appeared in the very popular magazine when I was a kid, Mad Magazine. Also, at about the same time, I taught a graduate course on elliptic curves and modular forms and turned my lecture notes for the course into a textbook that was published in 1984. Well, 1984 was an important year for me in elliptic curves because in December of that year, Hendrik Lenstra sent me a 2-page outline of his new elliptic curve factoring algorithm. This outline was easy to read and understand, and it hit me like a thunderbolt. Suddenly, Lenstra's algorithm escalated the level of sophistication of the math that could be applied to cryptography. It was natural at that point that I started wondering if the rich structure of the objects of arithmetic, algebraic geometry, not only the group laws on elliptic curves, but also on the Jacobians of higher genus curves, could be useful not only for attacking RSA as Lenstra had done, but also for constructing secure cryptographic primitives. Very soon after, in fact, the next month, in January 1985, I went to Moscow to participate in the exchange program between the U.S. National Academy of Sciences and the Soviet Academy of Sciences. In my earlier visits to Moscow, I participated in Yuri Monin's research group in number theory. But this time I worked alone. In the first place, Monin and his students by then had largely changed their field of interest from number theory to mathematical physics. And I'd also changed my interest to an extent toward cryptography rather than number theory. And that was a field which, as far as I knew, nobody did open research in the Soviet Union. And in fact, I would assume that the Soviet authorities would have been no more enthusiastic about open academic research on cryptography than was the NSA in the United States. Working alone then in Moscow, I soon saw that the Diffie-Hellman key exchange based on the multiplicative group of a finite field could easily be carried over to an elliptic curve group. And I convinced myself that the index calculus algorithms that provide the most efficient attack on the original Diffie-Hellman protocol did not carry over in any obvious way to an efficient attack on the elliptic curve group. But since I was really a newcomer to cryptography, I was not very confident about all of this, so I wrote a letter to Andrew Odlyzko describing the idea and asking him what he thought. Now, Andrew was the only mathematician I knew personally at that time who made major contributions to both pure and applied mathematics, which is much less common in those days than it is now. And I wrote him a conventional letter because there was no email then, and it didn't come to Moscow until many years later. And the turnaround for letters between the US and the Soviet Union was at least a month. And finally, I did hear from Odlyzko that he thought it was a good approach using elliptic curves, and that Victor Miller had independently come up with the same idea. During my semester in Moscow, the high point was my invited talk at the Moscow Math Society. My friend Tolya Fomenko, a well-known differential geometer and topologist, set up the invitation largely because he thought it would be really cool to have the first lecture ever given at the Moscow Math Society about cryptography given by an American. Some of the most famous Soviet mathematicians, Arnold, Gelfand, Shafarevich, Monin, and others would attend. And as a newcomer to cryptography, I was kind of nervous about making a bad impression because they couldn't just look at my what I knew about cryptography and say I was completely unqualified to be speaking at the Moscow Math Society about cryptography. But that didn't happen because what saved me was that most Soviet mathematicians knew even less than I did about cryptography. And I got good feedback from them after the lecture. So it turned out that most of what I described was actually new to them. I didn't mention ECC in this talk since I had not yet heard back from Odlyzko. When I returned to the US in the summer, I started attending crypto conferences, especially the annual crypto conference in Santa Barbara. I enjoyed the interdisciplinary nature of crypto. For the first time, I was learning from people whose background was in engineering or computer science rather than math, and who worked in industry or government research teams rather than in academia. At the same time, I met some of the famous names in cryptography of that era, such as the RSA trio, Ron Rivest, Adi Shamir, and Len Edelman, and also, of course, Whit Diffie, who had a special role at crypto running the rump sessions, which got wild at times with audience participation and heckling. The rump sessions became a little bit less rowdy after restrictions were introduced on what was allowed to be thrown at speakers if you didn't like what they were saying. So you were no longer allowed to throw full beer cans, but you could throw empty beer cans. And here are the four famous cryptographers at the time who I'm referring to. In those days, crypto was a lively, free-spirited event, perhaps in part because there was a certain forbidden fruit aspect in its very existence. Just a few years before, the NSA had made a heavy-handed attempt to get prior restraint to prevent open publication of cryptographic research. For example, in number theory, they wanted to preview papers and block publication when they contained results of cryptographic significance. Fortunately, that attempt at suppressing open research was derailed, but it led to great mistrust of the NSA and also led to a feeling that having open meetings like crypto was in a way an act of defiance. But this atmosphere, this freewheeling atmosphere at crypto seemed to change in the 1990s as the field got more professionalized with many careers at stake. And this led to intense competition to get large numbers of papers published and get contributed talks for oneself and when students accepted at the major conferences. And so in this way, crypto started to resemble the major computer science conferences, such as Fox and Stop. In addition, there were other conference series started in the 1990s with a narrower focus on a subfield. For example, the ECC conference series started in that decade. And gradually, many of the mathematicians, including me, stopped attending crypto and became more interested in some of the conferences that had more mathematical content. Now, I don't want to give the impression in this talk that I think mathematicians make particularly good cryptographers, because in fact, especially when we start working cryptography, and sometimes even after that, we mathematicians can sometimes be very naive about practical matters. In my case, this led to some serious misjudgments in my early crypto writings and papers and textbooks. First of all, for pedagogical reasons, I thought it would be nice to illustrate ECC using a curve for which the group order was easy to calculate, and you did not need Scopes algorithm, which was fairly complicated and couldn't be explained in detail to everybody. I use the example of the curve y squared equals xu minus x over the field of p elements with p congruent to 3 mod 4. It's a very easy exercise to show that that has group order p plus 1. At that time, I thought that the only security issue was that p plus 1 would then have to have a large prime factor. And in many cases, in fact, p plus 1 over 4 is already prime. Then we'd have a nice self-contained description of a secure choice of parameters. However, as Victor mentioned, soon after that, Menezes, Okamoto, and Vanstone showed how to embed that elliptic curve group into the subgroup of elements of norm 1 in the multiplicative group of the field of p squared elements, which that subgroup also has order p plus 1. This MOV attack was made possible by the same special structure that allowed us to make a quick count of the group order. So that reduced ECC for this curve to a traditional Diffie-Hellman protocol in a finite field. So what I thought was a nice ECC example does not, in fact, illustrate ECC at all. The second case of flawed reasoning in my early papers occurred when I proposed using the Jacobian groups of hyperelliptic curves of genus G greater than 1. Elliptic curves are the special case G equals 1. I gave examples of curves of high genus G over a small prime field P whose simple equation led to an easy computation of the group order, which in that case has magnitude p to the g power. So p can be quite small, p can be as small as you want, if g is a little bit large. So that's what I was interested in there. And I suggested that the Diffie-Hellman protocol might be even more secure when G is large, because high genus curves have greater complexity than small genus ones. Well, greater complexity is true in a mathematical, topological sense. For example, when one works over the complex numbers, the compactification of a genus G curve can be represented as a donut in the case G equals 1. In the case of an elliptic curve, can be thought of it as a donut shape, surface of a donut over the complex numbers when G equals 1. And when G is greater than 1, it will look like, can be represented as a surface with G holes, G donut holes in it. So in that sense, it's more complicated. But topological complexity by no means implies computational complexity. And before long, an attack on the discrete log problem for a hyperelliptic Jacobian group was found that becomes much more efficient for large G. So I had to hope that no one took my suggestion of basing their crypto on hyperelliptic curves of high genus over a small prime field. It was at crypto that I met Scott Vanstone and his star graduate student at the time, Alfred Menezes. And that was the start of a long and fruitful collaboration with them, and especially with Alfred. In 1998 to 99, I spent a year at Waterloo on leave from the University of Washington. In the 1990s, public key cryptography and computer security went from being a niche interest of a relatively small number of industry, government, and academic researchers. And Vic Miller showed you a picture of how small meetings could be on cryptography in the 1980s, to being a major concern in a computerized economy. There was fierce competition and conflict, but it was not spy versus spy type conflict, as in Mad Magazine that we liked to read so much when I was a kid. Rather, it was company versus company. Now, the RSA company started to feel threatened by the upstart company Certicom that Victor mentioned, namely the Canadian crypto company, at that time called Certicom, which was started by Waterloo people working with Scott Vanstone and had as its business model commercializing ECC. They were like the leaders of efforts to commercialize that type of cryptography. And it looked like ECC, which could achieve similar security levels to RSA with shorter keys, would expand its market share, especially in recently created constrained environments such as smart cards. In 1996, Alfred Menezes and I were jointly teaching a short course for graduate students on cryptography at the Mathematical Sciences Research Institute in Berkeley. Alfred showed me the part of the RSA website called ECC Central, which featured quotations from leading cryptographers connected with RSA that expressed skepticism about ECC. I was particularly impressed by the erudition of Ron Rivest's statement. He said that elliptic curves are a difficult and relatively obscure topic of study, and that, quote, trying to get an evaluation of the security of an elliptic curve crypto system is a bit like trying to get an evaluation of some recently discovered Chaldean poetry. Now, I didn't even know who the Chaldeans were, so I asked my wife Anne, who was trained as a historian, and she knew. They were people living in Babylonian biblical times. It turned out that the UC Berkeley Library had a volume of Chaldean poetry, and even the English translation was quite nice, readable and evocative. Well, it was customary at the end of the MSRI short courses to have souvenir t-shirts, a certain swag made for the participants with an appropriate slogan. I proposed that this swag have a picture of an elliptic curve with the words, "I love Chaldean poetry." And I also got some of the t-shirts, and I'm wearing one of them today. I don't know if you see this, but it's a little bit faded after 29 years. Okay, 2 years later, in early September 1998, I was visiting Anne in Phoenix, where she was a professor of women and gender studies at Arizona State, before going to Waterloo for the academic year. I received an urgent message that Scott Vanstone had called and wanted me to call back as soon as possible. This surprised me, since I never before got a telephone message from him, and I hadn't even thought that Scott knew how to reach me in Phoenix. It must be truly urgent if he couldn't wait until I arrived in Waterloo in just a few days. A few hours later, I received an email from Joe Silverman at Brown University that included a new algorithm for attacking ECC, and I immediately knew why Scott wanted to talk with me. And Joe is a leading expert on elliptic curves and the author of a widely acclaimed 2-volume textbook on the subject. This was clearly something serious. Joe called his algorithm ZEDNY, which is index spelled backwards, because in some sense its steps are similar to those in index calculus, but in the reverse order. Also, his algorithm uses elliptic curves defined over the rational numbers in a unique way, in an important way. Joe said he was agnostic about whether ZEDNY would be practical for curves over finite fields in the range used in cryptography. He wasn't ready to go public with his algorithm, but was only giving a few people advance notice, and apparently hoped that we would help him estimate the running time of ZEDNY for our curves, which of course we were anxious to do. Now, right before I left for Waterloo, I badly wanted to have something useful to say to my friends there who were allies in the RSA versus ECC conflict. I understood the reason for Scott's sense of urgency. Even though Joe had not yet informed anyone at RSA about ZEDNY, they'd get wind of it before long and would then start proclaiming from the rooftops that ECC was broken and that this shows the danger in replacing RSA with ECC in smart cards and other constrained environments. Thinking about the ZEDNY algorithm, I saw that a reasonably accurate estimate of ZEDNY's running time would likely depend on the heuristics of the conjecture of Burchett, Swinnerton, and Dyer for elliptic curves defined over the rational numbers. And I had no idea how to estimate those heuristics, so I was really stymied. But, however, the night before my flight from Phoenix to Toronto, I had trouble sleeping and returned to thinking about ZEDNY. Suddenly it occurred to me that even though I have nothing to say that could rule out practicality of ZEDNY in finding discrete logs on elliptic curves, I could do something almost as good. I could show that a minor modification of ZEDNY could be used to factor large integers. So if ECC was broken, so was RSA. This would certainly buy us some time. The RSA people would no longer be so eager to advertise the possible consequences of ZEDNY. Okay, and by the way, the reason why ZEDNY can be carried over from the discrete log problem to the interfactorization problem is very similar to the reason why Shor's post-quantum algorithm, which is basically for finding discrete logs, carries over to factoring integers. When I got to Waterloo, we immediately formed a small group of grad students and faculty at the Center for Applied Cryptographic Research there that would study the practicality of ZEDNY. Quite soon, I had a strong argument based on the heights of points on an elliptic curve over the rationals that ZEDNY would be incredibly slow asymptotically, that is, as the size of the finite field of definition approaches infinity. I presented this to the group and everyone was convinced. However, in cryptography, it's a common mistake, and a serious one, to be satisfied with asymptotic assurances. We really needed to test ZEDNY on curves in the range used in crypto, and this turned out to be a much longer, more difficult project than finding my argument for asymptotic impracticality. We collaborated closely with Joe Silverman, who advised us on the elliptic curves we should test and how best to incorporate properties of elliptic curves over the rational numbers, which form part of the algorithm. By sometime in the winter, we had sufficient evidence for curves in the range used in ECC. Already in that range, it turned out ZEDNY was extremely slow, even slower than exhaustive search algorithms. Joe conceded that ZEDNY was dead in the water. The ZEDNY drama was over, and for us at least, it had a happy ending. A decade and a half later, we went through another drama with ECC, and this one did not end happily. In 2013, WikiLeaks released NSA documents that had been obtained by Edward Snowden for For the cryptographic community, the most shocking revelation was that the NSA had inserted a backdoor in the dual elliptic curve deterministic random bit generator. That revelation made the front page of the New York Times. Then in December of the same year, we learned that the NSA had basically bribed the RSA company $10 million to install that backdoor version of a discrete bit generator as a default one in their BSafe computer security kit, thereby unknowingly making the name of their security kit quite ironic. This backdoor the danger of this backdoor was known to the designers of this DRBG, who had urged users to publicly verify that the 2 points P and Q that are used in their algorithm were chosen independently of one another. And that's because the backdoor basically consisted of choosing the second point to be a known multiple of the first point, where that multiple was known only to whoever put in the backdoor, in this case NSA. But NIST failed to carry out this verification, and a pseudo-random bit generator had been standardized with the backdoor. So I should say one other thing that happened soon after this, in 2015 actually, was that NSA abruptly and rather radically changed their stance on ECC. As Victor mentioned, they had recommended strongly the adoption of ECC about a decade earlier, and had been identified in the cryptographic community and in the public mind as big supporters of ECC. And so Alfred and I were mystified by the sudden change, what the urgency was, but their new policy was to tell people to abandon both RSA and ECC as soon as possible and adopt post-quantum techniques. So Alfred and I wrote an article for the IEEE journal Security and Privacy, discussing various possible speculative theories trying to explain the sudden change of policy by NSA in 2015. And we call it a riddle wrapped in an enigma, because it was really a mystery to us. I'm running out of time, so I won't talk about all four theories. I'll just mention the one that I think is the only plausible one out of those four. And that was that the NSA wanted to get away from a close association with ECC as quickly as possible after the DRBG scandal, because they'd been such strong supporters of ECC in the past that the association between ECC and NSA was rather tight, and was now associated in people's minds with deception and lack of trust. So they want to get away from that very quickly and have people stop thinking about ECC at all. But in my opinion, the rush to adopt lattice-based post-quantum crypto has some dangers in it. And in fact, I did some work jointly with Polish Sarkar in India and two former students of his, analyzing the main security reduction that's used to support provable security claims for learning with error lattice-based systems. And so we wrote a paper on the concrete analysis that is in the spirit of practice-oriented security that was popularized by Bellari and Rogaway. Practice-oriented provable security. So our paper, Concrete Analysis of Approximate Ideal Short Independent Vector Problem to Decision Ring Learning with Errors, we found several flaws in the main security reduction that the provable security claims relied upon. For example, the tightness gap in the reduction was huge, was absolutely astronomical. And so if you interpret it in practical terms, the lower bound you would get on the running time of the adversary had no practical value. Also, there were some implicit assumptions being made here, and for example, that the approximate version of ideal SFVP that arose in the reduction was very hard problem. Now, the exact version is widely believed to be a very hard problem, and there's evidence for that. But the approximate version of a problem that's hard in its exact version might or might not be hard. And that clearly depends on how large the approximation factor is. And when we looked at that in concrete terms, the approximation factor was quite large. And we didn't think there was any reason to believe that that would be a particularly hard problem. And there are other problems related to a rather unconvincing use of quantum mechanics, where a given state vector had to be preserved from one part of the algorithm to another, which is not standard, to say the least, in quantum mechanics. So anyway, this was our paper that supported our feeling that it was premature to go quickly to post-quantum crypto. Others have also expressed doubts that those post-quantum systems are ready for prime time, such as, for example, Dan Bernstein. And strangely enough, the cryptographic arm of the Israeli Defense Forces, called Matzah, has suggested that they're not as secure as some people are claiming. And in conclusion, I'll just mention two questions that are on my mind I don't know the answer to. One is, why was NIST in such a hurry to approve and standardize lattice-based post-quantum crypto? Was it simply a response to pressure from the NSA, or is there something else going on, that some other explanation for it? And next, why not standardize and recommend a hybrid system where an adversary would need to break both the elliptic curve discrete log problem and learning with errors in order to succeed? I think that would be a prudent step, because it would allow for the possibility that successful attacks on the standardized lattice-based systems in the next several years would not have a devastating impact, because ECC would still be secure and presumably will remain secure until really large-scale quantum computers are available. So those two questions are sort of on my mind at this point. And with that, I'll conclude and thank you for your attention.
Well, thanks very much, Neil. That was really fascinating and wonderful to see. Victor, I think you can come back if you're still there.
Okay, yeah.
So we've got a good half hour or a little bit more to have questions and discussion. I think what I enjoyed so much about both your talks is kind of evoking what doing research was like before the internet, when news traveled slowly and you had to know the right people to hear the whisper or to see the photocopied notes. I'm old enough to have slightly experienced a little bit of that. I remember the famous notes from Atkin from his improvements to Scoff's algorithm that was sort of mimeographed and passed around like holy relics. So that was fascinating, and I for the younger audience to see, how we had to suffer before the internet came along and made everything a whole lot faster. I've also, I think it was really great how both of you have talked about your kind of journey through pure math and into computing, cryptography. Neil, I really enjoyed how teaching got you. You got here because of your concern for teaching well and for engaging students, and I think that's a really great message to hear. So I guess I'll kick off with having presented this stuff, elliptic curves in the 80s. Did you expect at that time that you'd see it being used sooner? It took 15, 20 years before people really started using elliptic curves. Would you have expected people to have started using it much sooner when you were first doing that? Neil, we can start with you.
No, as I mentioned, I was not exactly up on practical things. I knew nothing about implementation. I knew nothing about the state of cryptography generally. So I saw it as very interesting theoretically, that you could use sort of highbrow mathematics and cryptography. But whether that would ever be a practical use, I just didn't have any knowledgeable opinion, and I didn't. I was still somewhat in the mode of assuming that I would never do anything useful in my research.
Right. Yeah. What about you, Victor? Did you think it would be picked up pretty quick?
No. Well, first of all, the cryptography people outside the government were still pretty small then. I mean, RSA was really the first company they know that really tried to commercialize cryptography. I mean, IBM did. So when I was at IBM, I found that IBM had developed the data encryption standard for the federal government, and I found that they did have a crypto competency center, and in fact, they were, well, to put it mildly, extremely discouraging of talk of fielding any other kind of cryptography than DES. And in fact, DES in their approved modes. I mean, I won't even go into stories about, because there was something that I got involved with at IBM where I and a number of others had made a huge impact at IBM because of using an adaptive data compression algorithm that I co-invented for use in their home terminal program. And one part of IBM wanted to supplement it with cryptography because they were perhaps worried about, confidential information going over the phone line. So I used a certain mode of DES, which wasn't one of IBM's approved modes, even though it was one of the ones in the NIST standard. And I got a lot of pushback from that. So I think, and that was the other thing, is people said, well, why didn't you patent this? Well, I'd already gone through patent with data compression. I won't even go on how my own feeling about software patents. But basically, IBM really wasn't really that interested. It was sort of an interesting idea. But I just thought I would sort of put it out there. I sort of cynically said that, when I went to, when I looked at cryptography, that I felt that it would be good for their intellectual development for cryptographers to learn a lot harder number theory.
Well, that seems to have worked. That's something actually that Neil, you mentioned in your talk, that you were when you saw Lenstra's paper on elliptic curve factoring, the idea that all this more sophisticated mathematics could actually be used for practical purposes. So I think there's definitely been a lot of progress in that idea. I think there's a lot more mathematics in cryptography now and in other areas. But I don't know, are we all the way there? Do you think that lesson is still, maybe back to Neil, do you think people still need to learn that serious mathematics and very advanced mathematics can be very important in practice?
Well, I don't think necessarily more advanced mathematics than is currently being used, but I think they have to learn it better. And in particular, I think it would be good to adopt a critical mindset about how mathematics is used, not only in cryptography, but in many other fields, because sometimes the superficial appearance of a proof impresses people inordinately. And if you examine it carefully, as for example, what I, at the end of my talk, mentioning about a paper of practice-oriented provable security that we wrote, raising questions about post-quantum crypto. Very often, at least it's sort of an opinion of mine, that an in-depth knowledge of mathematics is particularly important for avoiding fallacies and critically reading other people's mathematical claims and evaluating them without being swept away by the formal structure or by how many complicated constants they have in their security reduction or things like that. I think there's sometimes people's approach to mathematics is too superficial, in my judgment.
Can I add to that?
I know. Yeah, I mean, so even just recently, I mean, so when Dan gives his talk later, I mean, he's going to talk about zero knowledge proofs, and it turns out that besides making, a lot of the systems making heavy use of the pairing algorithm, I mean, there are a lot of applications to what are called expander graphs. And the construction of expander graphs actually involves a lot of rather sophisticated mathematics, all the way from property T of Lie groups to actually the unique expander construction. So I was just in my last job, they were interested in actually constructing practical examples of some of these expander graphs with particular properties. And I came across a paper which basically used, linear systems, to construct these, in practical. So basically people still need to know at least about I think it's very useful to know about, algebraic curves at the very least, and understand those, because I think they're a really fruitful source of constructions. And I mean, the thing is about elliptic curves, I think, I was being interviewed about this about a month ago. And, I said, one of the problems that happen with the adoption of elliptic curves is they seem so bizarre and exotic. And my point was that actually the software engineers who are implementing them really don't, they just have to have faith that the researchers have done their proper job, but the actual nuts and bolts of implementing them is only slightly more complicated than some of the other things, because it's just a matter of, manipulating various polynomials and things like that. So it's...
Yeah, I mean, it's funny. It used to be that elliptic curves were the hardest mathematics in cryptography, but now we have isogenies, we have ring LWE, we have things that are much more complicated for people to learn. Right. So it's the time moves on. Getting back to the sort of the mathematics and the sophistication of it, I think both of you have touched on how you really studied pure mathematics. You were drawn to pure mathematics. Especially Victor, you had all these fantastic photos of the sort of giants, the people, Tate and Maser and people like this that were never concerned with applications. They were concerned with beauty and structure. Maybe you can both say something about the sort of necessity of blue skies research and how there's got to be some, these structures had to be thought about by people long before they could be applied in applications.
Right. Yeah, I mean, I think it's necessary to prepare your mind. I mean, I found in my career, I mean, I can't talk about the specifics of what went on and, during the years I worked at the IDA Center for Communications Research, because most of our research was classified. But I found that, so one of the nice things about that place was that they, our staff were mostly PhDs in math. And they felt that it was really important to have a mathematical background. And their idea there was that almost any kind of math might be useful. So, for example, I had gotten interested, and we were given freedom to pursue it, even if it didn't seem to have anything to do or any applications at all. So a number of years ago, I got interested in a field called polyhedral combinatorics. And I just got interested in it, and then I read up on it and studied it and did work on it just because, it spoke to me. But I had no idea that it would have any sort of applications anywhere. It might, in some corner case. And I remember one of the last things I worked on when I was there is somebody had come up with a big computational problem they had, and they had reduced it to some sort of computation, which it turned out took a really long time. And one of my other, colleagues said, oh, well, Victor knows a lot about that kind of computation. Why don't you give it to him? And he told me about it. And it turned out the kind of computation approach was mixed integer programming, which I had done a lot, in, and it turned out that it solved the problem like immediately. I mean, but it was even much faster than I would have even imagined. So I was sort of scratching my head, and I wasn't going to leave it there because this intrigued me. So I looked at the problem, and it turned out that it had so much structure that I was able to dispense with a whole mixed integer programming and write a very simple, attack on it. And I only know about this structure because I've been studying polyhedral combinatorics. So I think it's really important for people to really study things that speak to them, so to speak, and spend their intellectual, ideas not just on attacking, the problems you want, but in other things, because I've always found that no matter what I look at, that somehow it always seems to come back to have some sort of application.
The connections are all there. Yeah. Neil, maybe you can speak to this as well a little bit. We were talking about the sophisticated maths, but you're also talking about not treating it as window dressing, but really getting to the heart of it. Maybe you want to say something about how you see pure mathematics, the development of it, and why it's so useful in applications.
Sure, I think it's a multifaceted thing. It's kind of complicated, often indirect, but I think one big advantage that mathematics has in preparing people for work in other areas is that it has a rather healthy disciplinary culture. There's not the excessive competitiveness most of the time that one sees in some other fields, including closely related fields. And you do feel a sense of freedom and a sense of, at least, maybe not if you're a tenure-track faculty member who doesn't yet have tenure, but you're sort of under some pressure to publish, as in all other fields. But for the most part, you don't feel under tremendous pressure. At least that's my observation. And then a lot of things, as Victor said, are serendipitous. That you meet someone or have a discussion or decide to look at something, and then it turns out sometimes much later to be exactly what you needed. So it's a little bit hard to pin down exactly what goes right so often about mathematics. It's like, I guess, who was it? Was it Teller or somebody who talked about the unreasonable effect?
Wigner, I think.
Pardon?
Eugene Wigner, I think.
Yes. Yeah.
Oh, yeah. That's it. Eugene Wigner. Yeah. And it is a little bit mysterious exactly why mathematics turns out to be so important in other areas. But I think also one has to guard against, especially in the U.S., there's a deep tradition of anti-intellectualism that's certainly coming to the fore again. And there are attacks on universities, there's funding cuts. We're having a big funding cut that, among many other things, is going to greatly reduce the number of graduate students we can support. So, this year we're only admitting 6 graduate students, which is about a third as many as we usually do. And that will not only have a terrible effect in teaching, because in our service courses we won't have nearly enough TAs, but also will just damage the department overall in many different respects. So this is just sort of the reality of sort of the outside world in the U.S. right now, and unfortunately there's a long tradition of that. And part of what worked against that tradition was when people came in, immigrated to the U.S., like from Europe in large numbers in the 1930s and in the recent past as well. And, there's that influence of that tremendously talented group of immigrant scientists and mathematicians that I think has played some role in keeping the U.S. on track, that is, from becoming too steeped in anti-intellectualism. But most people in our country don't necessarily believe that areas of music, art, and mathematics, and literature, and all these areas that don't have an immediate, obvious practical application are that worthwhile, and that's really dangerous, I think.
Yeah. Well, definitely. So there, she links really well with a question from Alice on the Alice Silverberg on the Zulip. She's talking about your political activism, Neil, that's been consistent for many decades as well, and she's interested in whether your research in cryptography and your political interests have ever been in conflict, and has there been a struggle to manage that conflict?
Well, I was amused, I'll put it that way, that the NSA was such a big ally on the issue of ECC adoption, and also my political activism didn't really take a personal tone. I mean, the people I knew at NSA and at other government officials, generally I found them very pleasant and have no trouble, and they didn't seem to mind me either. But so it's one thing to protest against what your government's doing. It's another thing to be hostile to people who are working for the government. Now, I'm a government employee of the state government, so it's not that there's going to be a contradiction on a personal level, but I did find it a bit ironic that our staunchest ally for a while on arguing for ECC adoption was the NSA.
Yeah. I'm not sure if that fully answers Alice's question, but we'll move on. So are you both, a question for both of you again, are you surprised how well ECC has stood up? I mean, you've mentioned a few weak cases, both of you, the supersingular curves, but basically ECC is pretty much held up as well as it could possibly have done so over 40 years of cryptanalysis. Would you have expected that back in the day?
I'm not sure. I mean, it's sort of interesting that essentially my original argument in my paper, which I think, Joe Silverman and he had a paper with Suzuki, which sort of expanded on my argument, trying, and basically said, well, it's sound. I mean, but this points out that what happened is that there was really only one, besides, a generic group argument, there was only one other argument which did better, which was an index calculus. And this seems to have persisted to this day. Now, it's not to say that somebody might come up with something else, but I mean, I think a number of people have looked at it. I think, cryptography, I think, ends up being a field like this, is that basically people propose what they feel are hard problems, and then they allow a number of what they hope are smart and dedicated people to take potshots at it. And after a while, if they get exhausted and haven't come up with anything, they decide that it's okay. I mean, that I don't think it's cynical to describe it that way. And so, I'm gratified that essentially, except for a hypothetical quantum computer, it still has held up. And in fact, it was sort of interesting when I was watching the talks that were given at the Simons Institute about zero-knowledge proofs. It's interesting that most of the zero-knowledge proofs, not all of them, but still a large number of them, still will use pairings and things on elliptic curves, and essentially it doesn't seem to bother them. I mean, I think that, for example, the blockchains, still use elliptic curves. They haven't transitioned to a post-quantum, so they don't seem to be as worried. I mean, should you be worried? I'm not a physicist, so I can't really make a definitive statement about the real practical viability of quantum computers. So I won't. Okay,
that's fine. But maybe on the same topic, Neil, I mean, elliptic curves is held up, but also, I mean, you have a paper with Alfred about the bodacious assumptions and some of these really elaborate assumptions that have been introduced exactly in pairing-based crypto. And I mean, it's crazy, but most of them seem to have held up as well. I mean, again, are you surprised that elliptic curves has been so robust against cryptanalysis?
Well, I think it's a really more practical issue, that as long as nobody thinks up a brand new approach, it seems that we don't expect many changes. But I think that one should be careful about assuming hardness of a problem that has not been exhaustively studied with people who are really good at the practical side, trying to find quick algorithms. There are problems that might seem at first to be very difficult, and you can't think of an attack right off. But I think in our paper we were bothered by some of the assumptions of hardness that were made without a sort of practice-oriented foundation. And I think you really need a combination of theoretical arguments, such as provable security reductions, and a lot of experience with practical computations attacking systems. You can't rely on just coming up with a clever version of a supposedly hard problem and say, you know, this is what the security of an attack on our protocol reduces to solving this really hard problem, therefore it can't be done. I think there are some real difficulties with jumping to conclusions about the hardness of problems, and also, of course, not taking a practical approach to security reductions. And that's not the least bit original with us. I mean, Bellari and Rogaway certainly saw in the early 90s about the importance of pinning down what a theoretical argument for security would mean in practice when you plug in the numbers and look at the objects of cryptographic size. Again, I think the theory has to be combined with concrete evidence. And I think in the case of elliptic cryptography, there's been a whole lot of sort of attempts in a practical sense to test the security. So there's reason to have some confidence there. But detailed protocols, specific protocols using elliptic curves, if one's the least bit careless about them, they can be completely insecure, like the DRBG that the NSA was able to backdoor. And also another problem that can sometimes arise is that things are designed and analyzed for a certain range of applications. They might be used in a completely different way as time goes on, and they need a new analysis. And there's an example that Alfred found, a kind of blatant example of a type of signature scheme which was widely accepted as secure, but then it could be used in a sort of backwards way in an auction, an online auction context. And there was a real security flaw in it. But as long as it was used in the same way it was when it was originally analyzed, everything was fine. But and so that could happen with elliptic cryptography, or at least with certain protocols, maybe new protocols that people come up with using elliptic cryptography. It's possible they could have problems.
Sure. Yeah. Probably a linking to another question in the Zulip was about is there anything that, you know, if we were doing elliptic curves now, if it had somehow by some freak of nature no one had known any mathematics, what would you do differently? Would you think if you guys were proposing elliptic curves now, or even 10 or 20 years after you had done, do you think there's things that you would have done differently?
I'm not sure. I mean, when I wrote the paper, I deliberately tried to use the least amount of advanced mathematics possible, and I actually gave it with explicit polynomials, so at least someone could implement it, because I thought that was, you know, a certain necessary state in case anybody thought of doing that. But as I said, I mean, cryptography was, and I guess still is, a field where people propose things, and then they hope that people, other, motivated and smart people will take potshots at them. Now, interestingly enough, despite their public, I mentioned Bert Kaliski, who was Ron Rivest's student, and despite the the public pronouncement from RSA of being extremely skeptical about elliptic curves, I mean, Ron immediately, the next year invited me to MIT to give a talk about it because he thought that this was really interesting and significant, and he obviously had one of his PhD students work exclusively about things about elliptic curves. So, but I think that's the situation. Is it's really necessary. I mean, you take what seems to be a well thought out proposal, and you have to try to analyze it. That's really all you can do. So I'm not really sure. I mean, I guess I wasn't interested in commercializing it. That wasn't my bent. I mean, Scott Vanstone certainly had that, and he ran that. But would I have done anything different in proposing it? I don't know. Maybe I might have, written more about it. But no.
You might have tried harder to get the vape pairing published.
Well, yes, I would.
What about you, Neil? Any thoughts on what you? I mean, you actually mentioned a couple in the talk that if you maybe a too easy special case again for pedagogical reasons.
Yeah, that was a mistake. I wouldn't do that again.
Well, actually, I did the same thing in my talk. At the very end, I actually had used, I think, the same curve or another supersingular curve with the same motivation that you had. But in fact, I said I would be a little skeptical of it because it seems to be too special. But that's all I said.
That's interesting. I didn't know that.
Yeah. You can look at the very end of my paper. I mentioned that.
I don't know if you want to add anything more to that, Neil.
Well, what started when I proposed, that was really the first thing I'd done in cryptography. And I was really quite naive and inexperienced. And if it hadn't been the first thing I'd done, had been 20 years later, of course I might not have gotten so interested in cryptography if it weren't for ECC. But if I had become interested in cryptography for some other reasons, and then after 20 years working cryptography, had the idea of ECC, then undoubtedly I would have done it in a more sort of sophisticated way, in a more sort of complete way, like I guess in my paper on the subject, I went into how you can encode a number, how you can code a message onto an elliptic curve or something like that. It's some very sort of naive stuff. But I don't think, basically it would have been that different.
Time's running short. There's a good question in the Zulip about isogeny-based cryptography, and has this been studied enough? Neil, you already alluded at the end of your talk to whether lattice cryptography has been studied enough, and how hybrid solutions are probably pretty sensible if we're trying to prepare against quantum computing. What do you think? Have isogenies been studied enough? Should we be trusting isogeny crypto? Any thoughts?
Well, I'm not that knowledgeable about the attacks on it and how serious they are, and how much of a shadow that puts everything in. I certainly wouldn't rule it out. And I know there is some history of types of systems that were attacked successfully with the parameters and the exact structure that was initially proposed, that later turned out to be serious contenders, like, for example, NTRU, which we thought was pretty much dead after various parameter choices were attacked successfully, but it apparently has had a reincarnation and is a serious contender for post-quantum crypto. And so it's possible. I wouldn't rule anything out, but I don't know enough about it. and specifically about the attacks on it, to have an opinion about how likely that is.
Yeah, and I mean, as far as isogeny-based crypto, I mean, it's funny because people, I don't think, will lump in these. So there was, what happened is that there was this one proposal for Psych, which basically got killed, but it really got killed not because it was isogeny-based, because there's this tension in implementation. Is you'd like to make your implementation as efficient as possible. And one of the things that gave Psych its vulnerability is that they made public extra information, which made the computation, made the encoding and all the rest of that much more efficient. But unfortunately, giving that extra information was what led to its downfall. But that doesn't necessarily mean that other uses of isogenies are bad. It was just that particular, use. And I think, is it really ready for prime time? No, I think it really needs a lot more work. I mean, the problem is that there are really not many people who are really seriously working on cryptanalyzing isogenies. I am. You are, but I mean, how many people in the world do you think there are? Maybe, two handfuls. I mean, maybe I'm exaggerating, but I mean, I don't think by very much. So
I think sorry to interrupt, but I think it's actually interesting to me how the community, when I first got into elliptic curve cryptography, there weren't that many people looking at elliptic curves.
Absolutely.
And I think that was even in the late 90s. It took, even 10 years after your papers.
Right.
There were a handful of people. They've mostly been mentioned. Menezes, Van Stone, Kaliski. There were a handful of people working on elliptic curves. It took a long time before there was the community. We've obviously got Tanya here in the call and Dan in the background. I think isogenies, the community grew at a much faster rate quickly. But still, I would also be cautious. The other thing I wanted to say about the isogeny attack, on Psych, was that it still required some really quite advanced mathematics. You were not going to break isogenies by staying in elliptic curve land. You really had to work with abelian surfaces and polarized abelian varieties, and you needed a whole lot of machinery that had been developed.
Right, exactly.
Mm-hmm. All right, we're pretty much at time, so I'm going to give you both just quickly. You've both said a lot of really inspiring things, I think, to younger researchers about learning mathematics. But anyway, one last piece of advice for a young mathematician or someone interested in mathematical cryptography that you haven't mentioned yet. So, Victor, have you got any words of wisdom?
Well, sort of in keeping with what I said before, I really think that go with problems, it's individual psychology. You have to really be enthusiastic about something. So go with something that really speaks to you. I remember that when I was a first-year graduate student at Harvard, the faculty took us out to the faculty club, and one of them, I think it might have even been George Mackey, said, "Well, now you're going to be mathematicians, so you should eat, drink, and sleep mathematics." But the point is that you have to, even if it doesn't look like it has anything to do with anything, if there's something that really grabs you, go with it, because it's going to pay off, if nothing else, in the mental discipline.
Neil?
Well, just to go back to what I said, I think it's necessary to have some critical thinking ability in going from mathematics to something applied like cryptography. And you can't, the big danger is falling for some hype or falling for some superficial analysis that, it might seem in the short range that there's no real incentive to be so critical and to examine things initially from a very skeptical point of view. But I think ultimately the habit of doing that will prevent you from making serious errors or from overlooking serious errors that other people are making. So I would say that mathematics is not window dressing. It's not just an excuse for hype. It's something much more fundamental. At least in cryptography, it is, and that's something that has to be kept in mind.
Beautiful. All right, I've had very much enjoyed this conversation and enjoyed your talks. I'm very confident that the viewers online will have enjoyed it too. So I thank you both very much. And congratulations on 40 years of a good idea still having legs. So we'll wrap up the live stream now, and I'll just remind everybody that it's a different link for the next session. So yeah, see you. Quick coffee break, and we'll be back in 15.